Welcome to our third session today. It's the last day of the digital WE days and we are looking forward to our next presentation. My name is Doreen Schäfer and I will moderate this session. Next to me, it's Mehta. Welcome.
Thank you.
He's a product manager for our product area Sensor Components. The topic of this webinar is Predictive Maintenance in HVAC, Role of Differential Pressure Sensors. Indoor air quality matters and clogged filters reduce efficiency. Let's see how smart sensing helps. The stage is yours, Ninat.
Doreen, thank you very much. Hello also from my side, everyone. I am Mehta, Product Manager for Sensor Components at Virth Electronic, and today we'll explore how differential pressure sensors play a vital role in enabling predictive maintenance in HVAC systems. Let's see the agenda, what we are going to go through today. First, what is HVAC, heating, ventilation, and air conditioning systems, and predictive maintenance in HVAC systems. And then we'll go ahead with how pressure sensors play the role in HVAC systems and how to choose the right sensor for your HVAC system, like a pressure or flow sensor, analog or digital sensors. And in the end, we will introduce to the differential pressure sensor portfolio from Virth Electronic. Let's start. So first keyword of the presentation, HVAC. What is HVAC? Heating, ventilation, and air conditioning. As the name suggests, this is a vital component of all the modern building and commercial and also private building, and also now residential buildings have all of them have a pretty more or less an HVAC system where you need to heat up the building or cool down the building and have a proper air circulation and ventilation. So this, in the end, this system regulate indoor air climate and air quality and the airflow of the whole building or the indoor area. What are the main components of the HVAC system? So most of you would know about them: thermostat, condenser or heating coil, compressor, fan, filters. You need these components to make a whole HVAC system, or also an air handling unit, so as to say. So more interestingly, for all of the buildings, this is a very important part of the buildings where this HVAC system usually needs to be regularly maintained, repair, or also now upgrade, because most of the buildings today in the world, more or less 40 to 50% are built before 1980s, and these HVAC systems installed in these buildings are quite old, and at some point they need to be upgraded because the old system consumes a lot of power and they are not working in the most efficient way. So in these days, efforts are being made to improve these systems, how to regularly monitor the airflow, to control the temperature, humidity, or also maybe a vibration of the compressor. And overall, this is our focus on how can we make these systems better. There is an interesting information from Australian government around 5 to 7 years ago, where it shows that HVAC system almost more or less contributes 40% of the whole overall energy consumption in an office building. And if you look into HVAC systems, what consumes most of the energy is the fans, heating and cooling units. So it is very important that we make these systems much efficient and monitor the parameters. So basically, the older systems were working like a switch. So for example, the heater is either on or off. So this in the end consumes a lot more power. So by continuously monitoring the environmental parameters like pressure, temperature, humidity or vibration, we can have a better system monitoring and better control over the whole HVAC system. How can we do this? How can we do the continuous monitoring is you monitor these environmental parameters with sensors. So basically the sensors become the eyes and ears of the whole HVAC system. And this gives us a very good control over the data to take the data-driven decisions and reduce the amount of power that the whole system consumes. And these are all the requirements for the newer systems where we need the HVAC systems to have a very low maintenance. They must be energy efficient and also connected to one another systems so that you can control them very easily. And you also don't want a very big downtime when you are doing the maintenance. So this is an important aspect of the modern buildings where HVAC systems needs to be installed in such a way so that they don't consume a lot of power, they must be low maintenance, and there should be very less downtime. But how do we do this, or how can we do this? So the traditional way of maintaining these HVAC systems is a preventive or corrective maintenance. So first we look at the left hand side where we have the preventive maintenance, where it shows that, okay, you have a routine checks. So a person or the operator comes and checks the system on a regular interval, where they check for any anomalies or everything, if everything is working correctly or not. This is time consuming and also increases the costs. Then there is a corrective maintenance. Corrective maintenance is basically fix it when it's broken. So when it stops working, you call the engineer to fix it, or the operator to fix the issue. So look for the issue and then fix the issue. So this is a downtime. This increases your system downtime. So for a big commercial buildings, you don't want a lot of downtime for such kind of systems. And that's where the predictive maintenance comes in, where you have access to real-time data and you have a continuous monitoring of these data, so that you can every time watch and look for anything which is not correct, or take actions where required at a correct time. So this reduces your downtime and also is not as cost effective, not as higher in costs. And as mentioned, how can we do this? How can we do this with the sensors, with monitoring this different kind of environmental parameters? So to monitor the pressure, you can use a pressure sensor. For monitoring humidity, you use a humidity and temperature sensors. And to check the, let's say, motor vibration, you can use a 3-axis or 6-axis accelerometer and gyroscope. So basically with the sensors, you can capture the data. Then you can transfer the data over any protocol that you can use, Wi-Fi, Bluetooth, or any other proprietary protocol that you want to use. So we are sending the collected data from point A to point B wirelessly, and then we can also use a cloud services to store the data and visualize the data. And with all of this data, you can ask these questions, or you can evaluate the data. Is my data looking normal? Is my vibration of my motor is okay within the range, or is it not in the expected range? Do I see any abnormal behavior in my system? With this, you can have a continuous monitoring of the data, and this is how with the sensors you can have access to the predictive maintenance. So the more the sensors you have, the more data you collect and more data monitoring you can do, and you can have a less downtime, and in the end this results in a better efficient system. As mentioned, today we are going to focus on the pressure sensor. So how are the pressure sensors centered in the whole HVAC system? Here are different scenarios where the pressure sensors are used in all of the HVAC system. The most common ones are ventilator and fan control, where you have a constant monitoring of the fan speed, and you have you make a slot in the tubes where the flow is reduced, where you can monitor the pressure between this slits on the left and right hand side of the slits to control the speed of a ventilator or fan. Then on this side you have a filter monitoring system, where you can install the filter you can monitor the health of the filter in the HVAC system. Then you have a static air pressure control, where you have the requirement to maintain a constant airflow or constant pressure during in the building. Most used also in hospitals, in the clean rooms, where you need a specific pressure control in certain rooms. And also variable air volume or a damper control, where also the pressure sensors are being deployed. Let's take a look at one of the examples first, the filter monitoring. Why filter monitoring is very important in HVAC system. These days we usually spend most of our time indoors. So as per statistics, we spend more or less 70% of our whole life indoors, and indoor has more pollutants than outdoor statistically. And after the whole coronavirus, everyone is aware about the indoor air quality and how important is the indoor air. So it is very important that we have a very healthy filter, because filter, you can say, are lungs of the whole HVAC system, because filters are installed in the inlet of the HVAC system, where the clean air or the air comes from the outside and it filters, and then the whole clean air is either heated or cooled down or ventilated throughout the whole house or whole building. So if you have a very dirty filter, then you have a reduced airflow because the filter is clogged, and this makes your cooling or heating efficiency worse. You have also higher energy consumption because the pump needs to work more harder to add on the constant airflow, and you will have a poor indoor air quality. And if the filter is very clean and it's changed too early, then you have increased material cost, which you wouldn't want, that you keep on changing filters even when it's not required. So it is very important to change the filter at the right time. And how can we do this is with the differential pressure sensor. So you have one each side nozzles of the differential pressure sensor connected, and then you monitor the pressure drop between the filter. So the higher the pressure drop, the indication is that the filter is getting clogged, and at some point you get the notifications that the filter, it's time to change the filter. So you find out the right time when you change the filter. So basically, if you see that how you can do this with the constant monitoring of the pressure drop between the filter, you have a linear increase in pressure, which is a linear pressure drop, which is a normal behavior when you have a filter being clogged. And when the filter gets more or less clogged after a certain threshold point, there your pressure drop starts to increase exponentially, and that is the point where you say, okay, it's a good time to change the filter, because after that there is a high chance of blockage. So this is with the constant data monitoring through the sensors, it is very essential that you get this information via the sensors, and you only change the filter at the right time. So basically, with this kind of sensors, you have a smart filter air filter monitoring system in your HVAC. Another example for this is fan failure or leakage detection. So another example is the static air pressure control, where you have one port of the sensor connected to the air vents and another is into the air, and you measure the constant airflow inside of the tubes. And whenever you have a leakage, there will be a change in pressure. So when you are monitoring constant air pressure inside the system, the green one indicates, okay, you have a constant airflow when the system is not leaking, and after when there is some leakage detected, then your pressure starts to drop. This indicates that either the pressure, so basically the pressure goes down and the system or the fan needs to push more air, so that speed also increases, or also you see a leakage in the system, and this is an indication that you have some problem, and before it goes too far, you can already fix it. So this also is a benefit how you can do a predictive maintenance on a running system. Another example for the fan failure detection, where you have a constant airflow, which is usually the also indication that your constant airflow is a constant air pressure, but then when a fan performance is degrading or it's not normal, then you have sometimes of usually abrupt fall of pressure, or also could be an increase of pressure. So this is also an indication that the fan performance is degrading or it is not normal. So maybe this is an indication that a system technician needs to look at this issue and fix it if anything needs to be done, because that could lead to a fan failure maybe in the future. So before your fan is being completely failed, which usually could stop your or halt your whole system, you can directly stop this failure happening with this kind of monitoring system. So this brings us to the question that, okay, now which pressure sensor should I use for such kind of system or for such kind of applications? Because there are different applications. You see most of the applications are also flowing air. So you could ask, okay, why can I not use a flow sensor? Because there are many flow sensors which are also being used as a differential pressure sensor. So basically The most common type of differential pressure sensor are like shown in the left, like a MEMS based, where you have a very thin membrane where the pressure is exerted on top, and then you have some piezoresistor on the sides which change its resistance. And these are like a MEMS based mechanical and electromechanical systems. And then there are flow based, where you have one heater on the center which heats up the air, and then you have resistors which change their resistance based on the temperature. So basically, when the air flows, the heated air also flows with that, and then the resistance of these two resistors change, and that from that you can also compute the flow or also the pressure flowing inside a closed system. So basically, how you can choose which sensor can I use for my system. So this also depends on your application. So for example, if you are using an HVAC system which is usually using air, then you can use either of the sensors, but usually the flow sensors are only calibrated for the air or oxygen or nitrogen, but not for all other gases. So for the MEMS based sensors are usually calibrated, or they don't need a special calibration based on which gas or air you are using, because it is not dependent on the density of the air. Then there are other also aspects. So for power application, so because the heater consumes always some constant power to heat up the air, so you need a bit of more power to run these sensors rather than this sensor, because this is kind of a passive, or they don't require any own energy to run. And also for ultra low pressure or flow applications, the flow sensors are better because they have a more or less a zero offset at a stable state, but this has some offset because of the mechanical membrane, and which will introduce some offset at the 0 point. So basically, this is also where the flow sensors are good. But for example, in case of contamination, which you see a lot of time in the HVAC systems, where the air is usually not fully clean, so you have a small contamination in the flow sensor, since the air flow completely through the sensor, and if this thing is blocked with some dust particles, then the sensor will completely stop working. On the other hand, if you have a membrane based sensor, then it could be that the contamination is always deposited on this one, which will increase maybe the offset of the output, but it will not make the sensor stop working. So this is also an important information to make understand or make sure which sensor I should use for my HVAC system and what are my requirements. We are going to focus today more about the MEMS based pressure sensors. What are the MEMS based pressure sensors? So they as explained, you have a thin membrane and you have a piezoresistor, and with the stress from the top side, you have the piezoresistor either in tension or compression, and based on compression or tension, the resistance changes, and then they are connected basically in a Wheatstone bridge. And Wheatstone bridge will be in imbalance when there is a lot of pressure or a very small change of pressure, and this will lead up to output of millivolt of electrical output. So basically, the change of the pressure will lead to the change of the resistance and will add on or give you a millivolt output. And usually this output is analog, not compensated and not calibrated, and in the production this in the end needs to be calibrated or compensated. The good thing about this sensor is very high linearity, because of they are using resistors, and resistors behavior is usually linear, and they are also easy to produce and at a very low cost, but they are basically sensitive to temperature changes. That's one of the drawback. And when we look at this kind of sensors, what are different kinds of sensors available in the market? So this is also a very interesting topic, where you have different packaging or different types of sensors available only in the piezoresistive type of sensors, where you see, okay, the very basic ones is the MEMS cell, which is only the Wheatstone bridge. So this is, as we saw in the last slide, which is like uncompensated, not calibrated, and analog millivolt output. This is like a bare die silicon package. Then you have a one more level added, where next to the MEMS die you have some laser trimming resistors and some amplifiers, so that you can connect it to your microcontroller or host controller. So this type of sensors are like passively compensated for some certain temperature, because we saw that they are also temperature sensitive, so they need to be compensated for a temperature, and then you do this compensation at a specific temperature as per the application, but they are still analog output. So for example, if you have an application that requires the operation at 45 degrees and the compensation is done at 25 degrees, then overall your sensor is not fully calibrated at 45 degrees where you are going to use it. So you might get false values or not so accurate values. And then the third type is the MEMS die is directly connected to a full IC, and this IC usually has an amplifier, multiplexer, analog to digital converter, and also a small RAM where you can store some data as well. So usually with this IC you can produce a sensor which gives you a fully calibrated and fully compensated output. So there are different kind of sensor available, from a single sensing cell to an integrated complex sensor system, and this is also plays a very important role in which type of sensor you are choosing for your application. Very good example against analog and digital sensor is that also analog sensors have a very high accuracy because you have a direct change in millivolt output, but then it depends also how good your resolution is, or also the analog sensors are usually also more in current consumption, and also in your end system you require more components on your PCB board, so it increases your bill of materials as well. Also, if your system is requires high resolution and lower power consumption, then a digital sensor makes more sense. So basically you have to choose the sensor which as per your end application requires. How can basically then a digital sensor help in terms of this HVAC system is that, for example, you have a normal sensor which is directly communicating to a microcontroller, and then you send it the continuous data over, let's say for example, Wi-Fi to the cloud to do the monitoring. So now you have here an algorithm where if a pressure value changes after some threshold, then it is sending to the cloud, and then here you can build your behavior algorithm where you see, okay, this is the time where I have to take an action or preventive measures. What happens here is that it requires a constant communication between the microcontroller and the sensor. So your microcontroller is always active, and this also adds more current consumption, and here you are sending also higher data rates and you are sending more packages on the data. So you also need higher processing power. So on the other hand, if you have a fully digital or a very smart sensor where it has more functionalities, where it might be possible to add the threshold algorithm directly on the sensor itself. So basically you add more processing power on the edge device in the end, and then you have more so the sensor works more independently and the dependency on the microcontroller is reduced, and this gives you basically more energy efficient solution. So basically here the sensor directly sends a signal when the pressure drops, or with your algorithm you see the abnormal behavior, and sensor only alerts the microcontroller at a certain amount of time. So rest of the time your microcontroller is inactive, which is reducing your current consumption, and also your when you are sending this data from point A to point B, your data packages are lesser data packages, so this gives you also higher energy efficient system. So not just for the predictive maintenance, but also this reduces your overall energy efficiency on the sensor level itself or on the board level itself. So choosing a right smart sensor for the HVAC makes in the end a lot of difference. So now we come to last part of our presentation, where I want to introduce to our pressure sensor portfolio that we have right now in our portfolio. So we have differential pressure sensor starting from 0.1 kilopascal to 1500 kilopascal. So from a very low pressure range to high pressure range, and all of them are running on 5 volt, or also some of them are running on 3.3 volts with 15 bits of resolution, and they are ready to interface with the microcontroller with I2C and analog or SPI output as well. So these are all fully calibrated and temperature compensated sensors which have on-chip temperature sensor as well to compensate for any change of temperature as well, which will give you a very effective and reliable values also at lower and higher temperatures. So there is no additional calibration required basically. And we have 6 pressure ranged fixed configuration, and they are all available. But if so basically, yeah, they are all suitable for battery-driven and real-time monitoring application, and also can be used for wireless data transmissions, and also for sensor connected sensor network. So they can also be connected on a same I2C bus with more than one sensors on the same bus. Let's say, for example, differential pressure, temperature, humidity, and acceleration sensor. If you need more than this, the fixed sensors, then we are also able to individualize the sensors based on your application. You can either have a 3.3 volt or different resolution, or you can have an alarm generated directly from the sensors, which we talked at edge application. So we can fix the threshold for a, let's say 50 kilopascal sensor. If the threshold crosses 20 kilopascal, then the sensor alerts the microcontroller directly, and the next steps can be taken from the operator or from the technician. So these are the possibilities that we have. And for the quick prototyping, we also have the evaluation board that you can connect to. So the sensors are either in straight nozzles or on the side nozzles. For the straight nozzles, we have an adapter you can put on top. Basically, this helps the sensor for a higher for better mechanical stability, and this makes the sensor more stable and increases safety. Basically, this gives the less stress on the solder joints when you are connecting tubes directly. So if you are connecting tubes through the adapter, then there is no stress on the solder joints, because solder joints are not meant for the mechanical stress and more for the electrical stress. So this is possible, but if your application is space effective in HVAC, if this is necessary, then we have a side nozzles where you can connect the tubes directly to the sensors as well. So if you need this kind of support, this is also provided from us. The adapter is also available for you to check and quick prototyping. So that brings us to the end of the presentation. If you have any questions, feel free to ask. Thank you very much for your attention, and I wait for Zorin.
Okay, thank you very much for your informative presentation. I liked it. And first of all, before we start with the questions, I will share your handout. So everyone should be able to see the handout now. Right. So let's have a look at the chat. And I would love to start with a question I just had. So we are going to answer my question first. Can these MEMS pressure sensors be used for liquid media?
Depends on how the sensors are made. So the sensors that we showed from the Wirth Electronic, what we have in our portfolio, are only intended to be used for air, clean dry air, and non-corrosive media, so no liquid. But there are sensors which have basically some kind of a gel coating on top of the electronics, which makes the whole electronic secured, and then you can use them also for the liquid or some corrosive gases. So this needs to be taken care. What is the requirement is in your HVAC system, usually you have air, basically. So you have air, basically you have air flowing, which is not usually, sometimes the air is also humid. So it depends if you have a higher amount of condensation, and the risk of condensation reaching into the sensor could potentially make the sensor at risk, or the sensor might stop working. So basically, either you can choose also to have some kind of filters to deploy that doesn't let the humid air inside, humidity inside the sensor, and only make the air inside the sensor. So this could be also one solution, because the gel coated sensors are also in different kind of a price category, but they give also a bit of delay, because you have some media in between the sensing element and the air.
Thank you, well noted. Thank you very much. So let's move on. Herbert has a question for you. Do you have MOQs for the sensors?
For the sensors that we have in our portfolio, which are already released and which we have on stock, there is no MOQ. But the sensors for the customization or individualizations, there is, or there could be an MOQ of I think 500 pieces, but I have to check. But this you can also send us an email to get to know what are your requirements for the customization, and then we can have a deeper look into your application and help you out to choose the right sensor configurations and also decide on the MOQs.
Perfect, thank you. It's nice to know that our experts have time for you. And also maybe we just make the next one from Herbert as well. So we answered all of his questions. Is there a possibility to get a custom solution?
So in terms of a sensor solution, yes, there we can provide some changes inside the sensor. For example, the standard pressure range we have is from 0 to 100 kilopascal. And if your application requires, let's say, only 0 to 50 kilopascal, then we can do these changes. Or even some solutions require wider operating temperature ranges that we can also customize and calibrate the sensor in our production as per the customizations possibilities, which also can be checked with our BDMs and also with us, our R&D team.
Perfect. Thank you very much. So let's get in contact with our experts and make your customer solutions get real. So there's another one from Edwin. The differential pressure sensors sample with their internal time base. Can I trigger the sampling externally to get a crystal stable rate? Application measuring low frequency sound and noise.
I have to check because I'm not sure at this point. If you can check the frequency of 5 to 50 hertz, this is something that I might have to change with the R&D guys, and I can get back to the answer, but I have to check at this point. Yeah.
Perfect. So Edwin,
but maybe what I can add is the sampling rate of the sensor is fixed during the production, and we can afterwards we cannot change it. So if you need a specific sampling rate, then we have to check first internally what is the sampling rate, if it is possible, if the IC is capable of doing this, and if after that if you have enough power or less noise. So if this is possible or not, but this I cannot answer it completely 100% right now.
Don't worry, Edwin, don't worry. We have our experts and we will send them your question and you will receive an answer in the next few days. Also, if there are any questions left, feel free to send them to us into the chat. We will answer them afterwards. Thank you very much for your attention and I hope you enjoyed the session. Thank you, Ninat, for your presentation. You did a great job and thank you for your time. And we hope to see you at our next session at the Digital UE Days.
Thank you very much. Bye-bye.